what we're going to do in this section is we're going to take a look at the kinetic energy specifically of a rotating object. Okay, and in this problem, or in this, I should say problem, this section, we're going to specifically look at what kinetic energy is with regards to. So if we're looking at work, if we're looking at power, so we're going to see how we have kinetic energy and we relate that to work and power just like we did with translational. So let's start first with some definition. So if we recall, we know that the kinetic energy of a rotating object is 1/2 I omega squared. And if you recall, this is analogous to translationally K equals 1/2 mv squared. That was what we thought of earlier. So because of this nature where we have the linear motion and the rotational motion that are very analogous to each other, we'll see that if we think about our formulas in linear motion, they're also related to rotational motion. So let's think about what those would be. So if we want to find work in a linear sense, we would say it's the integral of f dx. That was the work done, and that would go from whatever the initial position was to the final position. Now, it's very similar for rotational work. We take the rotational work and we say that that's equal to the integral. Instead of force, what do you think we're going to use there? What have we been making analogous to force when it comes to rotating things? Torque, yeah. And instead of linear motion, we have rotational motion. So instead of dx, what are we going to use to represent rotational? Yeah, d theta. Okay, and we're going to go from our initial angle to our final angle. So again, the work done is very much the same as the work done with linear motion, except now we use different variables to calculate it. Questions so far? I'm just trying to give you guys the formulas. I'm not going to go through derivation of every one just for a little bit of time. This derivation, just so you know, is on page 282. Okay, on page 282. And it starts by using the integral formula for work, for one-dimensional motion, and then integrating that to go to rotational. Power, if we remember, power equals, and if you recall, in this case, this was dw dt, which in linear motion could also be written as F times V. F times V. Now, if that's the case, F times V, we could say to ourselves, if we want to find the power for rotational motion, we could say that power is still dw dt, because that's the change. That hasn't changed at all. Work is still work, time is still time, depending upon whichever direction we're going. But what we'll now see is that instead of F times V, F becomes torque again, and V becomes omega. The work done, if we look at a constant torque, just like we had constant force, if we had work done and it was done by a constant force, we would say it was just the force times what? If it's a constant force, work is force times, yeah. So in terms of rotational, instead of force now we have torque. Now, instead of distance, what we have is this, and this is a little bit tricky to think about. We're going to have our delta theta here. Let's talk about why that one makes sense. Why is it delta theta? Because we're not looking actually in this problem at the, we need to recognize what the final theta is. If it's spun around like 10 times, now we know that's 3,600 degrees in revolution. And we have to take that full 3,600 and subtract from that wherever it started. So when you think about distance and displacement with linear motion, it's very similar in this case. This delta theta, we really need to know what the final position is, and we don't want its coterminal angle. So for example, like if the final angle is 380 degrees, that's the same as 20 degrees, right? From our coterminal angles, we know that, but we're not going to use 20 degrees there. We're going to use the 380 as our final position. And if the initial position was, say, negative 15 degrees, we're not going to use positive 315, which is coterminal with negative 15. So we have to make sure that here we're looking at like a distance traveled, but rotationally. So the rotational angle that has traveled. So if you loop 3 times, your delta theta is going to be 360, 360, 360. It's not going to be 0 degrees. You see what I'm saying there? So I'm not looking at the angular displacement. I'm looking at the angular, almost like the arc length. It's really the overall arc length that this object has traveled through. So if it loops 3 times, we can't call that 0 again. We got to call that triple 360. If it loops twice, well, that's just going to be 720. And that'll be our delta theta for this problem. And the key is to recognize that, remembering that this is distance in this formula. So this has to do with the actual like full arc length that it's rotated here. So far, so good? Questions so far? Go ahead, Matt. Yeah, catch up later, okay? Good luck with your thing. I don't know what he was going for. I forget. He said Purdue. I don't know if it was an interview or just a tour. All right. The last formula here is our kinetic energy. So if we think about the work kinetic energy theorem, we said with linear motion that work equals the change in kinetic energy, which was 1/2 mv final squared minus 1/2 mv initial squared. And that was linear motion. So it's going to be the same thing with rotational. Our change in kinetic energy, or work, equals change in kinetic energy, 1/2 I omega final squared minus 1/2 I omega initial squared. Oh no. Okay, give me a sec, guys. Let me reconnect the iPad. Yeah, you're right. It's not there. That is so weird. Give me 1 second, okay? Why is this happening? All right, let me just disconnect Zoom. Hold on a sec. Try to. So we're going to revisit this arrangement we had last class. Okay, we had this pulley, right? And the pulley had a mass hanging from it, and we took a look at this problem to analyze. We did this with 10.6 and 10.7. But now we're going to take a look specifically at kinetic energy. So we start by saying, let the disk in figure 1019, this is right out of your text, by the way, just so you know, this is page 284. 284. Let the disk in figure 1019 start from rest at time equals t0, and also let the tension in the massless cord be given as 6 newtons, and the angular acceleration of the disk be negative 24 radians per second squared. What is the rotational kinetic energy K at the time t equals 2.5 seconds? So, if we're looking for rotational kinetic energy, what do we need? Let's start with that. What do we need to find rotational kinetic energy? And let's do it the easy way first. We'll do another way in a minute, but let's start with just regular kinetic energy formula. For kinetic energy, we need 2 things. What are they? Good. And in rotational? Close. It's not mass. Yeah. Remember that moment of inertia, I? So if we want the kinetic energy of a rotating system, we're looking at 1/2 I omega squared. Now, we're looking specifically at the rotational kinetic energy of, in this case, that disk when it's rotating. So we have to figure out, when it is rotating, what is that angular velocity going to be, right? We don't have omega in this problem. I think we calculated it's a disk, so it's 1/2 mr squared. So we can start by replacing this 1/2 with 1/2 mr squared times omega squared. And we're trying to figure out this kinetic energy at a time that's given. So how is that time going to help us? How is that time going to help us in this problem? Oh, you're on the right track. We're given the angular acceleration, though, so we're not going to get that, but you're on the right track, Chip. Yeah, to calculate that angular velocity. And what's the initial angular velocity going to be in this problem? Yeah, it starts from rest. So that's important to note, that we have to figure out what omega is, and we have the time, we have the angular acceleration, so we can figure out the final omega value, or omega f. So before we can get into this part, let's put that on the side over here, right? So let's say that we know that the angular acceleration equals the change in the angular velocity over the time period. And I'm just rewriting A equals delta V over T, right? It's the same thing as A equals delta V over T, but I'm doing it in rotational terms. I know the alpha value, so I'm going to multiply by T. We know that omega final minus omega initial is really just going to be omega final, because that's going to be a 0 there. So if we want to figure out the rotational velocity at the time 2.5 seconds, all we have to do is do negative 24 radians per second squared, and multiply that by 2.5 seconds. Notice again, time is so nice. Time is never a function of the rotating aspect, the translational aspect. Time is simply time. So it doesn't have to change units, and notice how it's used in both cases, linearly and rotationally. So that's what our omega f value is going to be. What is that going to give us? Let's see, 48 plus 12, 60, negative. Okay, so now we have the omega value. We're trying to find the kinetic energy of the system at this moment. So we can go ahead and plug in what we know now. 1/2, we know the mass of the disk. The mass of the disk right now, it was somewhere in the problem. I think it's given earlier on. Hang on, let me just see. 2.5 kilograms? Yeah, 2.5 kilograms. And again, that was not given in this problem, by the way. That mass was given in figure 1019. 1019, yeah, in 1019. So that's where the mass of that was given. It's not given in this problem, which personally is kind of annoying. The book does this a lot, but they do it to save pages. They refer to old figures and stuff all the time. So 2.5, the radius of that disk, also given from earlier, is going to be 0.2 meters. That quantity is going to be squared times the omega value of negative 60 squared. I'm dropping units, obviously, because everything in this problem that I'm writing right now is in terms of either meters, radians per second, kilograms. I've got all my standard units applied here. So it looks like we should get around 90 joules. I don't know if this is a rounding or if this is an exact value. Okay. So that's the method that I would personally take to solve this problem. And what's interesting, though, is you'll note, if you look at your book, if you're following along with the book right now, the book then goes on and says, we can also get this answer by finding the disk's kinetic energy from the work done on the disk. So let's do it the second way, just so we can see how the work kinetic energy theorem will play a role in this problem. But again, I would personally have solved it this way, because this is by far the easier way to do it. So let's take a look at the second methodology here. Okay. So the second part says, let's take a look at this by finding the, again, work done on the disk. So we know right away that we have to think about, what does work done mean, right? The work done is the change in the object's kinetic energy, but what was the kinetic energy to start? It was just yeah, exactly, very good. Because it wasn't rotating to start. So we are literally having this statement here, which tells us that if we want to find the kinetic energy in the system after 2.5 seconds have elapsed, we could really just find the work done for the first 2.5 seconds. Okay? Now, to find the work done, though, for the first 2.5 seconds, we have to ask ourselves, well, what's happening in this problem? First, the tension in the cable. The tension in the cable. That value is a constant. The tension in the cable, what is it, 6 newtons, I think, right? Yeah. is 6 newtons. Where is the tension in the cable coming from? Tell me again where the tension in the cable is coming from here. Yeah, the weight of the block, okay? So the tension is really Fg pulling down from the block. So the tension is a constant. Next, we know that, and we could jot these notes down if it helps, right? So tension is constant. Oops. What else is a constant in this problem that we can use with tension or the force to find something else? What else is a constant in this problem? Gravity is a constant. Good. Not going to help us to find something else though right now. What else are we going to need? Angular acceleration. Okay. And we'll discuss why that's a constant in a moment. We need a little more information to validate that one. There's one other thing that's a constant still that we haven't actually written down yet. What's that one other thing? Geometric property. Spence? I can't hear you. You're muted. I think you're saying mass. It's not mass. I mean, mass is constant. Sorry, yeah, it is. But the radius. And let's talk about why this matters. So the radius is also a constant. Because the tension and the radius, are constant here, what other value is therefore a constant? Which leads us to say that the angular acceleration is also a constant. If I've got the force acting on an object rotating and the radius that force is acting at, what's the other thing that's going to be constant in this problem? Yeah, because we've got force, right? The force times the lever arm or the radius r. So we think about this problem, this force, let me zoom in so you can see it a bit better. Okay, this force that's pulling down right here, this is the tension, that's a constant right there. If that's a constant and so is r, then the overall torque applied to this rotating object is going to be constant. The reason we want to know that the torque is constant is because if the torque is constant, then the angular acceleration is constant. That's why I said when M said angular acceleration is going to be constant, just to validate that that's going to be a constant there because the torque is constant. What do we know? We know that So because the 0 for the omega I times t is there and the 0 for the theta I is there, the entire problem simplifies a bit. So if we want to figure out the final angular distance that this thing has rotated, we can simply use 1/2 alpha t squared. So that can go in for the value over here, so let's keep carrying this down. And we can get a number for that. That's fine too. I'm just substituting in for now. Let me actually put the arrow pointing right there more. Now, if we had a starting position, we could have just solved this equation on the right. We could have solved this equation here for theta f minus theta I. Okay, so we could have solved this, moved the theta I over, and just got theta f minus theta I by using this entire piece here, and then plugging that whole thing in for theta f minus theta I. So we don't have to solve for theta f in this problem, but we want to know how much it's changed, what that, like Chip said, angular distance traveled was. So we can use this minus this to get the quantity and plug it in right over there. But again, because this is 0, it drops off. It makes it a little bit easier on us. Now, what's the torque going to be equal to? Well, torque is equal to, again, the force applied at a given distance. And that distance might be r, or the distance from the fulcrum. So when we look at this, we're going to say, all right, this is going to be omega equals, now this is going to be a force times the distance times 1/2 alpha t squared. The force in this problem is tension. Right? The force in this problem is tension acting on it. So we know that this is going to be the actual tension involved here. This is going to be the R value, which is given in the problem. I think it was given as a capital R in the diagram. And we still have the 1/2 alpha t squared. But what do we have to recognize here? Alpha, if I recall, is negative. The torque applied in this problem is going to be also negative. Because I think about this, right? The torque is being applied. Let me zoom in so you can see it a bit better again. Come on, I got to zoom in. Oh, there we go. The torque is being applied on this side, which means this thing is going to rotate clockwise. And clockwise we consider to be a negative torque. And we also consider this to be a negative angular acceleration. So the double negative is going to end up canceling. But let me show it so we can validate that here. So this here should be a negative in front, and this quantity for alpha right here will be also negative. So this negative and this negative will make this a positive amount of work done. So what are we going to get? We should still get 90. It should be the same answer. Let's see. We've got the tension is 6 newtons, so that's going to go in for T. We've got the radius again as 0.2. We've got the 1/2 there. Alpha is going to be negative 24. And then T is going to be 2.5, and then we square that. Yeah, so that'll be 90 here for this one also. But again, if I'm looking at this problem, right, and I really reanalyze this, it's clearly obvious that the first way we did the problem is a lot easier. This was only done so that we can kind of show how the work kinetic energy theorem works as well. And if you guys recall from earlier this year, we talked about how how with linear problems, you can use the work kinetic energy theorem sometimes. Sometimes you can use other things. You don't always have to be using the work kinetic energy theorem if there's other ways to do it that are easier. So in this problem, I would not use the work kinetic energy theorem. I would just go ahead and find the overall kinetic energy at the given time that's listed. Okay, this is very similar to a problem where you have your kinematic equations or your dynamic equations like Newton's laws versus work kinetic energy theorem, like the sliding across a floor with socks on kind of problem. You could have done that 3 or 4 different ways. The same thing applies here. So on the day of the test, you got to ask yourself, if you're doing a problem, like, all right, A, am I taking the most ideal route? And if I'm not, what can I do differently? Or B, can I just continue with this route at least because I've started it already? So if you're doing it one way and you think halfway through, oh, there's another way I could do this also, you might be already halfway through and it might not be worth going back and changing it at that point. Is that clear what I mean as far as like the two different methods? And I would think about this also because the test itself now, they gave the format. Did anyone look at it yet? Has anyone gone to the AP website? Okay, so the format is going to be, I think my numbers are right, a 25-minute question that talks all about how you would set up a problem, the equations used, possibly having analytical variable solutions, numerical values at one point in time, using some sort of derivative or integral along the way, all into one problem for 25 minutes. And then the second problem is going to be 15 minutes, and that's going to be like those lab problems where they give you a scenario and say, how would you design this lab to accomplish this task? So those are really the two parts of the new test that they're creating. So it's really one big math problem and one lab setup type problem, okay? As opposed to the three problems they used to do, two of which were math and they were lighter, and one that was a lab problem. Now they're doing one big math problem and one smaller lab type problem. Okay, all those details are listed on the AP website if you want to see that also. Kara, what's up? So the way it's going to work for this exam is that I'm pretty sure, is that you're writing it, and then you have 5 minutes to take a picture and upload it. So they're giving everybody, even though it says 45 minutes, they're giving you 25, and then 5 to upload, and then 15, and then 5 to upload. So it's really 50 minutes actually, not 45 for the physics exam. So you have the 5-minute buffer at the end to upload. So, I mean, if you aren't done and you just keep working till the end and you run through the 5 minutes, you're going to get a 0 on the problem. So keep in mind, you got to upload something. If you spend the extra 5 minutes and do work and don't have time to upload, they're going to say, sucks, you should have uploaded when the time was called. You can have a formula sheet out. You could have sample problems all over the place. It's open book at this point, right, when you think about it? So that's up to you guys to think about your timing when it comes to these problems. And if it were me and I were like thinking about, okay, how can I prepare for this? I would probably make like a sheet of like sample problems of different types. Like, okay, here's the pulley problem with a mass hanging. Here's a pulley with an inclined plane. Here's a frictionless pulley. I'm going to tell you now that there's no chance that they're going to have a pulley problem and they're going to say, oh, a massless frictionless pulley. It just doesn't make sense at this point because now that we know rotational stuff, they're probably not going to emphasize a massless pulley. So I would not go back to the chapter where we did dynamics earlier this year with forces and look at those problems again that had no mass to the pulley and no moment of inertia and all that stuff, because it's not going to happen on this kind of a test now. If that were a multiple choice, though, then it's different, right? For a multiple choice, you probably want to know those other scenarios where there's a massless pulley or a massless rod, for example. Now all the rods or all the members we're looking at are going to have mass. Okay, so think about how you want to categorize the problems that you're going to study with and what you might want to have as a reference near you so that you see, okay, this is this type of problem. Let me just look at this. Okay, that's it. I got it. And then you get right into it. Okay, so preparation for this exam is going to be huge, especially because of the fact that it's open notebook. So you're ready to go and you're not flipping through your book trying to find a similar problem and wasting 10 minutes doing it. No, go ahead. Yeah, that'd be a good idea. Maybe something I could do in the next couple days is just come up with all the types of problems and assign a different problem to each person as like a practice. And then you guys can upload those problems to me and we could look at them together and say like, all right, let's make a running list of all this. That'd probably be a good idea. We have until May 11th, by the way, just so you're aware. There is technically another date for this, but I think you should all take it May 11th. I don't think you're going to want to take it in the beginning of June when you're dealing with like, if we have postponing graduation, all that kind of stuff that's going on, but it's kind of up to you, but May 11th is the date for it. So yeah, I think, Max, that's a great idea. Maybe, I don't know, in the next week, I can come up with those problem types. Maybe I'll even talk to Mr. Donachek and get his feedback on it, what he thinks could be the most highly expected problems we'll look at all the exams together. And then maybe I'll just assign a problem for each of you guys to work on, and then we'll put it all together as like a, resource. It's a good idea, Max. Okay, so let's get into another problem. So let's look at the second problem here. So there's a good amount of writing here. This is similar to one of the homework problems you guys are going to do. So it says a thin rod of 0.8 meters and mass of 0.2 kilograms is suspended freely from one end. Okay, so we've got a ceiling here right off the bat, and we've got this rod that's suspended from one end. Okay, at the top, and I'm going to put like a little red dot here to show that it's suspended from that end, because the next part's going to say it is pulled to one side and then allowed to swing like a pendulum. So that means that there's got to be like a fulcrum right there, right? Or some sort of a pivot point we have there, an axis of rotation at the top. Passing through its lowest position with angular speed 3 radians per second. So we can say that this object, right, is going to get raised up like this, and then it's going to swing back and forth. And when it's at the bottom here, its angular speed is 3 radians per second. Okay, here's the length of 0.8 meters. And the mass we know of the rod is going to be 0.2 kilograms. Let's see. Neglecting air friction and air resistance, find the rod's kinetic energy at the lowest position. Not too bad. And how far above that position the center of mass will rise. So, first, let's talk about this. It's a thin rod hanging. Where's the center of mass, assuming it's uniform? Yeah, in the middle. Now, what if it's not uniform? Let's say it's not uniform for the moment, okay? And let's say that the center of mass is down here instead. See where I put that X? Let's say it's 3/4 of the way down. The problem does not ask us where it starts and where it ends, the center of mass. What does it ask us? Say again, Chris? Yeah, how much further it up it rises. So really, we're looking at the difference between those two blue X's in vertical height. So our goal for the second part is to find this delta right there. Okay? So again, the second part is the harder part. The first part is the easier part for this kind of a problem. The first part asks us, okay, let's see. Find the rod's kinetic energy. All right, so kinetic energy. If I want kinetic energy, I can do it 2 ways. I can use work, like we did last problem in the second part, but I don't think I'm going to use work here because then I have to figure out the force of gravity, at what angle it acts, how does that produce a torque on here, and that's a lot more work than it's worth. So let's use the first kinetic energy formula. So we can start with kinetic energy equals 1/2 I omega squared. Now, if kinetic energy is 1/2 I omega squared, and we know it's a thin rod, what are we going to use for the I value? If it's a thin rod, what is the I value for this? I don't even have it memorized, guys, so if you want to look it up, you can. Let's see, I'm pulling up the table myself right now. I think it's 1, no, where are we? I think it's 1/3 ml squared, because it's about its end, not the... Well, for this problem, this is not a thin rod rotating about its center, right? It's a thin rod rotating about the end. This is one that we might want to add to our table, actually. So if you guys want to jot this one down, I think we derived this. Yeah, we derived it the first day when we were doing moment of inertia, and we watched that video with Flippin' Physics when I was broadcasting from Loyola and you guys were home. And I think that we wrote down that the moment of inertia of a rod about its end is 1/3 ml squared. So I've got K equals 1/2 times 1/3 ml squared times omega squared. And then everything else is given in the problem. I don't know what the number is. Can somebody help me out with the value here? What do we get for a value here? And my units for this would be? What are we solving for, Kara? Good. 0.19, verify. I'm assuming it's right. Perfect. That sounds good. Okay, let's look at part B now. Let's take a look at part B. So how far above the position does the center of mass actually rise? So let's ask ourselves a question first. If an object is rising and falling back and rising and falling back, what kind of a problem is this that we've seen many times over and over? Yes, good. Recognize this. At the top. And the reasoning, because there's no what in this problem? Correct. So the key is to recognize that we've got the energy initially equals the energy at the end. And there's no Q loss, there's no work done by friction, there's nothing done at the hinge, there's no air resistance, or else we would recognize that we had to have lower energy every time we swing through. It would keep decreasing. So anyhow, we know that we could say that the bottom, when the pendulum is at its vertical position, we'll call that initial. So we'll say it has all kinetic energy in the beginning, and it has no potential energy in the beginning. And then at the end, it's got no kinetic energy, but it does have potential energy. So pretty much, as Spencer just said, the kinetic energy that we have in the beginning is going to equal the potential energy that the rod has when it's at its top point, or its highest point, I guess we could say. Now here's the thing. We have to think about this, and we have to set something equal to 0, right? Because we're trying to find the delta H in this problem. So where is our ground level in this problem? What are we calling ground level if we assume that there's no potential energy when the rod is in the vertical position? What are we calling ground level? Be careful with your answer here. Good. Both of you guys. Very good. The initial center of mass, or where the center of mass is before it swings. Nice. So let me use yellow here. I'm going to put that dotted line like I've always done. So again, we called the center of mass some arbitrary point on purpose because this does not have to be a uniform rod. So that dotted line is where we're going to say there is no potential energy right there. And then the question is, what is the height it rises to? Well, that's why it's got potential energy once it rises above that. And we're looking for the delta H denoted in the diagram there. So we've got initial height is 0, right? H0 is 0. And we're looking for H final, really, or Y final, we could call it. So we know that K0 is a value we have, so I don't have to put a formula in for it. We figured it out in part A. The height is going to be mg Y final. And again, Y initial was 0, that's where we dropped off, and Y final is really H. So in essence, we're solving for Y final, or H. So it'll be K0 over mg. And that will give me the height, or Y final. So 0.19 divided by the quantity, what, 0.2 times 9.8? What do we get for a number here? 0.097. 0.097, that looks right. And that's in meters. Oops. There we go. So we don't care in this problem really where the center of mass is. It's never asked of us, and we can't determine that actually because we don't know about the rod's mass distribution. If the rod was heavier toward the bottom versus the top, or more dense at the bottom than the top, then the center of mass would be skewed in that direction. We care about how the center of mass has changed. And remember that conservation of energy applies to particles, and then when you have an extended body like this, it really applies to the center of mass of that extended body. So conservation of energy that we just used can apply to anything, a point particle, but because we have a longer object, we have to always be looking at the center of mass. We have to always be looking at the center of mass. Let me see anything else for this problem? No, let's go on to the next one. I want to finish with one more, and this is timing, all right? So we're doing it right now. I didn't give you guys a break. Sorry for today. I totally forgot. Feel free to remind me next time. I'm not going to do a break now, though, because then we're just going to run out of time. So the last problem I want to look at here, and this is a bit trickier. It says a stick of length 1.3 meters is held vertically with one end on the floor and is then allowed to fall. So imagine it being held, right? You're holding something up like a 2x4 and then you just let it go. Find the speed of the other end of the stick just before it hits the floor. So obviously we're not looking, assuming that the end on the floor does not slip. So we're not looking at the end that's touching the floor initially, right? We're looking at the end that's at the top, right up here. So it's going to do this, right? It's going to just release and then fall. And we want to know the speed of this end of the stick just before it hits the floor. So we have to look at this problem and think to ourselves, how can we use, clearly we're going to be using kinetic energy because we have kinetic energy in this section. So how do we use kinetic energy for this kind of a problem? What are we doing? We're looking specifically at the point, right? At the very top and seeing what its velocity be at the bottom. But what kind of energy does the stick have and where is that energy referenced from? So let's start by drawing it first. Okay. Now for this kind of a problem, it does matter where the center of mass is. It does matter. Why does the center of mass matter for this kind of a problem? Good. Keep going with that, Chris. Okay, but how do we find that kinetic energy? You said we're going to use the point to find the kinetic energy, but you kind of skipped a step in there. Yeah, so in this problem, the change in height is not going to be the full 1.3 meters. Keep that in mind. Even though the point that we're really interested in is the end, right? We're interested in this point right here at the end. We know it's rotating about the point in yellow, and we know that its actually center of mass as far as potential energy is smack in the middle. So I'm putting an X for the center of mass, a red dot for the point that we're interested in, its velocity, and a yellow dot for the pivot point right now. So we know that in the beginning of this problem, if this stick is standing, its center of mass has some height, but it's not moving. So what kind of energy does this problem start with? Yeah, it's all potential in the beginning. It's definitely potential in the beginning. Now, we're going to call the ground level for this problem because it's logical. It makes sense to say that when it hits the ground, it's got no potential energy left. So let's make sure that we denote that. That's U equals 0 there. How am I doing on time, by the way? Don't let me go. Oh, okay, we're still good. We got a couple minutes, 4 minutes. So that's the ground right there. So when this object, meter stick, 1.3 meter, whatever it is, hits the ground, we know that it's going to be moving the instant before it hits the ground. So it definitely will have kinetic rotational energy. Kinetic rotational energy. So we can say this is equal to K final. Now, what else do we have to do after that? Well, we can find the kinetic energy at the end, and then we got to find the speed. So we'll talk about how to get that speed in a little while. So let's start this problem by looking at what we've got. So we know that the potential energy in this problem is mg 1/2 L, and we'll call this whole thing L. That's the potential energy, again, because it's the center of mass is halfway up the actual 2x4 or whatever it is. And then the kinetic energy at the end of all problems is 1/2 I omega squared. Now the key in a problem like this is to recognize, like, what are we going to call I? All right, what are we going to call I in this kind of a problem? It is, again, 1/3 ml squared, L, yeah. And the rationale is that we have a stick of a certain length. We're not given any information about its radius, so we know we can consider it a thin rod, and it's rotating, again, about its end. My guess is that there's going to be part of the question will be a rod rotating about its end. It shows up on a lot of problems, and it's one of the traditional ones you'll see. So it's good that we're seeing a little bit more of this, but if it were a different shape or a different item, we'd use something different. But it's rotating about its end, so yes, we're going to use the 1/3 ml squared for that. So the 1/2, I go back, okay. The 1/2 on both sides cancels. And then let's go ahead, we've got mgl equals I omega squared. I, again, is 1/3 ml squared. Okay, and now the last step. What are we trying to find? The speed of the red point, not the angular velocity or angular speed, but the speed, it says. So what kind of speed is that we're looking at? It's a bit trickier. Yeah, the linear tangential speed at the top of the stick. And remember, as the stick is falling, right? Here, let's put an image here. As the stick is falling, its linear velocity or its tangential velocity is always tangent to the path, right? That's what it would look like. So we're looking for that velocity vector, and that vector is going to get larger and larger until it hits the ground eventually. So here we have the same vector, and now that vector has gotten larger. So it's speeding up the end of the stick pretty much. So we're looking for the tangential speed. So we need to replace omega with its equivalent value. Who remembers, what is omega equal to? I know, right? There's a lot going on in this problem. This was the formula here at the top. From earlier on in sections like 10.1 to 10.4, it was V equals omega times R. Now, R in this problem is the distance from the point that is of interest to where the pivot is. So R is really L. So this formula becomes V equals omega L, right? And if we solve for omega, it's going to be V over L. And our goal is to find out what V is in this problem. I know we're running out of time, so if you do have to go to class, you can get, we're just at the bell now, so you guys have 3 minutes to go. Let me just finish this. We'll see that it looks like in this problem, what's going to happen here? Oh, this is an ml squared, not ml cubed, sorry, it's ml squared. What's going to happen in this problem here is we're going to notice that the L squareds are going to cancel on the right side. Do we all see that? Take a look here, that's an L squared, and that's going to be L squared also. So these L squareds are going to both cancel with each other. So the resulting equation will be mgl equals 1/3 mv squared. And then to get the m canceling on both sides, that's nice, right? Boom, that's gone. Which I could have done earlier, I guess, right? And then finally, the last step is to recognize that we got to get v. So it's going to be 3gl under a square root. 3gl under a square root. So that number, whatever it turns out to be, I don't know. So it's just going to be 3 times 9.8 times the length of the meter stick. So it turns out that it's independent of mass. It doesn't matter how heavy this object is, it just matters how long the object is. The length of the object is what gives us the tangential velocity there. Okay, this was a heavy problem, so this is the kind of problem where you're going to want to have to recognize what's going on with energy methods and at the same time looking at it rotationally. Okay, I will assign homework from 10-8, so that homework will be due in our next class, and I'll see you guys again, I think, on Wednesday of this week. We don't meet on Friday because it's Good Friday, so I'll try to assign 10-8 homework like as soon as possible in the next couple minutes. So to work on that for sure. I think I also put an Ed Puzzle video you should look at, okay? I know you have class. I'm sorry, guys. But good job with this today. And please let Matt know to look at this online, okay? All right. Have a good day, guys. Whoops.